So today we will start in lecture 6. We will talk about discrete sampling and analysis of time varying signals. So today lecture is talking about sampling, just sampling. Okay. So if we have a signal like the continuous signal here, we want to represent this signal in the computer. We cannot represent it like that in the computer. We have to capture the value of the signal at discrete time, like the right figure here, that I see that we have taken a sample here, another sample here, and so on. So when we perform a measurement, we have a transducer, and we know that from previous lectures that the transducer's job is to convert the measured the measurements into an electrical signal. And we take this signal and we sample it using a digital computer. Normally, we record the continuous signal at y of t, they call it y of t, and the signaled signal, which is, or discrete signal, which is, we call it ys of t. And this is the t, which is the time. This is the time, and this is the value of the function, or the value of the, you can say the voltage of the signal, or the amplitude of the signal. We have also, we can also define another expression, which is the sampling frequency. The sampling frequency is defined as the reciprocal of delta of t, or the we can say f of s or fs equal to 1 over delta of t. We can say this one is strange. It is not just one. It's representing 1 second. You can say 1 second, and then this is delta of t. We cut this 1 second to multiple delta of t. So here we have the delta of t is represented at the time between two samples. The time between two samples is delta of t. And we can define the frequency is how many samples we can make in 1 second. This is the real translation of the sampling frequency. Just to know how many samples can we make in a specific specific second. 1 second, how many samples? This is the sampling frequency. Uh, our objective is to, in the sampling, our objective is to be too near to the original signal. So we have the original signal as a sine wave in this dotted red signal. You see it. We need to make samples to make too near the signal, the original signal. So we have, you see, we have a signal here. We have a sample signal. The sample, the signal is too near to the original signal because we are making the sampling at a frequency too near to the original frequency. So if a signal is sampled and recorded relatively rapidly, the sample data will closely resemble the original signal. That is the objective of the sampling, is just to make or to copy the original signal in a discrete space. But we can say that we will undersample the test data if we sample very slowly. We sample very slowly. If we sample very slowly, we will take a sample here, another sample here. We should take sample here, another one here, another one here, another one here. But here we are very slow. We take one sample here, one sample there, one sample here, and another sample, and so on. And if you see, this is the resulting signal. This is the resulting signal. This is the sampled signal, or the sampled data. Or you see, the original signal is in red, and the sampled signal in blue or dotted blue. We don't have, they are not equal. They are two different. They are two different. Why? Because we sample very slowly. We cannot create the original signal and its original shape. We are too far from the original shape. So if we sample too slowly, as we see in the figure, a recorded data will present a distortion from the original signal. We'll have a distortion, or you can say uh, noise, is noisy signal. Such a distortion will introduce some measurement errors. That's why we should have a criteria to define what is the best sampling rate. What is the best sampling rate in accordance with the original or original signal frequency. For the sake of implementing very professional sampling, we should have a unit, we call it sample and hold. This unit is very important. So if we see that we are here, we are sampling at this place, we are sampling at that place, and if we don't have, we are holding a voltage here. We are holding a high voltage, for example, 10 V. If we don't have the sample and the hold unit, we will go down to zero and then jump back to the next sample and jump it down to zero and so on. This will create a very distorted signal. But I don't want to jump down. I just want to continue from the last place that I was there. We do that, or this job is done by the sampling or sample and hold unit. So the sample and hold is very important just because we don't want to be down to zero. We just want to keep the voltage at the higher level and jump to the next level and so on. Not to jump to zero and then quit.
application update. Once he's coming tomorrow, he will handle. لا يعني السيرت يلا شغال يشتغل اليوم. شغال بيعمل ايه؟ ريزولف؟ يا عم شفت ابديت بتاع.
Okay, I muted all the students. So if you need any help, you can send me a message on the chat. Okay, because some of the students are opening their mic, they don't recognize that they are opening their mic. Okay, so here we continue. We have a 10 hertz sine wave signal. We have 10 hertz sine wave signal. You see, we have the start of the signal, the start of the cycle. We call it cycle. Start of the cycle is here. Okay, I can draw it with the color. The start of the cycle is here, and then we continue up, 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 and so on. Then we go to the top of positive value, and then returning back to the zero, and then going down, 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 down to the negative value, the negative amplitude, and then returning back to zero again. And this is a complete cycle. This is one cycle. This is also only one cycle. Oh, so if we want to continue this way, we count how many cycles out there. We have here 2, 3, 4, 5, 6, 7, 8, 9, and 10. You see, this is 10 at 1 second. This is 1 second. So we can say this is the frequency of the signal, which is 10 hertz, which is 10 hertz. 10 hertz for what? Because we know we have 10 cycles or 10 cycles per second, 10 cycles per second, or 10 hertz. Okay, this is the original wave that we are working with. Our objective is to sample this. So suppose we are sampling at rate of 5 hertz. We are sampling this way. We will create the sampled frequency. It will be a straight line like this one. It's very strange because we are undersample the sample, the original signal. One could conclude that the sample signal has a constant value and the amplitude of the signal is misleading. The amplitude means the distance between zero and this value, and the resulting amplitude is misleading because it is not real one. Because if I change the start signal, if I change this one, change it to, for example, upper or lower, this is a misleading value. It will be another line, and this line is higher or lower. So it is not an interpretation of the amplitude. So this is not correct resulting signal because we are undersampled the signal. This behavior occurs if the wave is sampled at any rate that an integer fraction of the base frequency. It is a very small frequency. Yeah, it will be a line when we are using a fraction of the original frequency. So we have 10 hertz, the original one, which is this one, is 10 hertz, and 5 is a fraction of 10 because 5 is half of 10. So if the frequency is a fraction of the original frequency, the sampling frequency is a fraction of the original frequency, this means we will have a straight line like that. But if it is lower than 10 hertz, we will see different samples and different types of frequency that will be created. What about if we are sampling over than 10 hertz? Suppose we are sampling at a rate of 11 hertz. This is going to create another frequency. This frequency is very strange because it is very low frequency compared to the original frequency which is one 10 hertz. This is about 1 hertz because a complete cycle will start from the beginning to the end, or even not to the end. This is going to be less than one 1 hertz. So the resulting is going to be the frequency is about 1 hertz, and the difference between the sampling frequency and the sampling rate. It means that we if we sample at a higher frequency, we will get a lower frequency, resulting lower frequency. If we are sampling as a fraction of the original hertz, we will create a straight line. Okay, and if we are working with a sample rate is about 18 hertz, this is going to create a sample frequency like the one you are seeing here. It is like is not constant frequency. Yeah, we can say it is it has a specific frequencies about 10 hertz, but the amplitude is different in different places. So here the amplitude is lower than the points here. So at a sampling frequency of 11 hertz, the reconstructed sine wave appears to be 8 hertz sine wave. That is, the frequency of the sine wave reconstructed from the sample data is still different from that of the original signal. These incorrect frequencies that appear in the output data range are known as alias frequencies or aliases. We can remember this name because we will need it in the coming slides. The alias frequency. The alias frequency is like somebody is coming from space. We don't expect to have this frequency. That's why we call it alias frequency. The alias frequencies are false frequencies that appears in the output data that are simply artifacts of the sampling process that don't in any manner occur on the original data. So here, yeah, it means that it's very strange because which frequency is suitable to be the sampling rate? Which frequency is better to be the sampling rate? That, okay, let's take a final example. What about the double of the frequency? For example, the sampling rate with 20.1. Take care of the point one because it is very important here that the point one will do this drop in the frequency, in the amplitude, sorry, in the amplitude. If we don't have this point one, we will have the same, approximately the same frequency as the original signal. That means we can sample as a rate of double the frequency, and that is the Nyquist theorem. This is the Nyquist theorem. A continuous signal can be represented by and reconstructed from a set of sample values, providing that the number of samples per second is at least twice the highest frequency presented in the signal. So the best frequency is double the frequency. The best frequency for sampling is double the original frequency. We can say F max that if we have different frequencies in the original frequency, we get the maximum frequency and double it and then make it as a sampling frequency. Nyquist theorem is appeared here in the energy diagram for the signal energy. So here, if we have this is the original signal, we should have the sampling frequency to be double the original frequency. Uh, so no overlap between the energy of the original signal and the energy of the reconstructed signal. Here we have the energy is overlapped because we are sampling at a frequency lower than 2 f max. Then we have an overlap here. This overlap will make a distortion and will create too many alias frequencies. We don't like to have alias frequencies. We need the original frequency to be reconstructed. That's it. We just need to have the original frequency reconstructed. We have 10 hertz and we want exactly 10 hertz. We have an amplitude and we need that amplitude to be recreated. Okay. This is very important shape here to make you imagine the sampling when we take a sampling as a very low frequency. We see that the sample points in the square, the green square, the green squares here, that will create another completely different frequency, which it is not the original frequency, because the original frequency we can say if this is 1 second, we have 1, 2, 3, 4, 5. This is 5 hertz, and the resulting is 1 hertz, just one cycle in second. That's why we say this lower frequency sampling is not good. We should have double the frequency, which is if this is 5 hertz, we should sample at 10 hertz. High frequency signal be sampled low sampling rate may cause the fold the sample data. Fold means that we just ignore some frequencies and we get a lower frequency signal. This phenomenon is known as aliasing. And aliasing example, we have here the original signal, which is 10 hertz. This is a sampling frequency as 100 hertz. This is a sample frequency as 27 hertz, and this is at 12 hertz. The high frequency, for example, if we have a high frequency like this one, 30, this is we just we have the original we have the original frequency, which 10 hertz, which is 10 hertz, and the sampling frequency is 30 hertz. This will create a completely different frequency too, and we don't also like to have this frequency. Finally, we have an example. We have an example here. the alias formulas. So if A is alias frequency and Fn is a folded frequency or Nyquist frequency, we have Fn equal Fs over 2. This means the sampling frequency, the Fn, which is the Nyquist frequency, should be the original frequency over 2. So, sorry, the sampling frequency over 2. This means Fs is equal to 2Fn. Fs is equal to Fn. This is the Nyquist theorem. Is Fs equal 2 multiplied by Fn. We need Fn, so we say Fn is equal to Fs over 2. And Fa is Fa over F of n multiplied by F of n. These are the basic rules here. And we have a question here, or an example, numerical example for it. So if we have the sampling frequency to 250, we expect to have alias frequency, but we don't know exactly the value of the alias frequency. We can calculate it. Fa over Fn, and you see Fa is the alias frequency. We want to calculate the alias frequency, and we know the criteria. Fa over Fn, which is Nyquist frequency, is equal to zero point 0.5, and F of Nyquist equal to 250 over 2, which is the original frequency, which is the sampling frequency. This is going to give us 125. Fa, which is the alias frequency, equal Fa over Fn multiplied by Fn, which is zero point 0.5 multiplied by 125. This will create 62 hertz alias frequency. This is going to create 62 hertz alias frequency. Okay. Uh, the the lecture today is very short, just for the sake of the time we are here at Ramadan, and كل سنة وانتم طيبين. And يعني if you have any questions, you are with me.